Welcome to Math Zone African Motives. In this tutorial, we will be diving into the topic of third-order determinants. Our main goal is to help you understand how to find the minor of an element within a 3x3 determinant. We will cover what a third-order determinant is and, most importantly, we will learn how to calculate the minor for any element inside of one. By the end of this video, you will be able to confidently identify the structure of a third-order determinant and calculate the minor for any of its elements. First, let's answer the question, what is a third-order determinant? A third-order determinant is also known as a determinant of order 3, or simply a 3x3 determinant. This means it has 3 rows, 3 columns, and therefore a total of 9 elements. Now, let's visualize this structure. A determinant is represented by square brackets, or often just by vertical bars containing the elements. For a 3x3 determinant, we have 3 rows and 3 columns. Notice the notation. Each element is labeled with 2 subscripts. The first subscript, represented here by I, indicates the row number, and the second subscript, J, indicates the column number. So, for example, a 1, 2 is the element in the first row and second column. The structure shows our 3 rows, row 1, row 2, and row 3. It also shows our 3 columns, column 1, column 2, and column 3. So, a 3x3 determinant is a grid with 3 rows and 3 columns. There are 2 main methods for evaluating a third-order determinant. The first is called the diagonal expansion method, and the second is the cofactor expansion method. For this course, we will focus exclusively on the cofactor expansion method. To use this method, we must first master 2 key concepts, minors and cofactors. This tutorial is dedicated to understanding minors. So, before we can even begin calculating a 3x3 determinant, we need to make sure we have a solid understanding of how to find the minor of an element. This is the essential first step. Let's define what a minor is. We're now in section 1.3.2, the minor of an element. Each element in a square matrix, including a determinant, has its own unique minor. The minor is essentially a smaller determinant that is associated with a specific element. The definition states that the minor of an element, denoted as m sub ij, is the value of the determinant that results from deleting the row and the column in which that element lies. Let's make this visual. Suppose we have a 3x3 determinant D with elements A through I. If we want to find the minor of element E, which is in the second row and second column, we would physically remove or ignore the entire second row and the entire second column. What's left is a 2x2 determinant, consisting of the elements A, C, G, and I. The minor of E is the value of this smaller 2x2 determinant. To calculate it, we multiply the diagonal elements and subtract. So the minor of E is A times I minus G times C. So, to recap, finding a minor involves 2 steps. First, ignoring the row and column of the element, and second, calculating the value of the resulting 2x2 determinant. Let's apply this concept to a general 3x3 determinant in our first example. Given this 3x3 determinant with elements A1, 1 through a 3, 3, we need to find 2 specific minors. First, we'll find the minor of a 1, 1, and then the minor of a 2, 2. Let's start with the first part. We need to find the minor of the element A1, 1. Remember the rule, delete the row and column where the element is located. Element A1, 1 is in the first row and the first column. So, we will ignore or delete all the elements in row 1 and all the elements in column 1. This action is sometimes called row elimination. After this elimination, what are we left with? We have the 2x2 determinant formed by a 2, 2, a 2, 3, a 3, 2, and a 3, 3. So, the minor of a 1, 1, which we write as m sub 1, 1, is equal to the value of this 2x2 determinant. Now, how do we evaluate a 2x2 determinant? The rule is to multiply the elements on the main diagonal and subtract the product of the elements on the other diagonal. So we have a 2, 2 times a 3, 3 minus a 3, 2 times a 2, 3. This gives us the full expression for the minor of a 1, 1. Next, let's find the minor of a 2, 2. We'll follow the exact same process. First, locate the element a 2, 2. It's in the second row and the second column. So, to find its minor m sub 2, we must delete or eliminate all the elements in the second row and all the elements in the second column. What 2 by 2 determinant remains? We have a 1, 1, a 1, 3, a 3, 1, and a 3, 3. These four elements form our new, smaller determinant. The minor of a 2, 2, m sub 2 is the value of this determinant. Now, let's evaluate this 2 by 2 determinant using the diagonal rule. We multiply the main diagonal, a1, 1 times a 3, 3, and subtract the product of the other diagonal, a 3, 1 times a 1, 3. This gives us the final expression for m22. The previous example was general. Let's work through a specific example with real numbers. This is example 1.3. We are given this third-order determinant with numerical elements. We need to calculate the minors of three specific elements, 3, 2, and 1. So, our tasks are to find the minor of 3, the minor of 2, and the minor of 1. Let's begin with the first element. We need to find the minor of the element 3. First, find where 3 is located in the determinant. It's in the first row and second column. So, we are looking for m sub 1, 2. Following our rule, we will delete row 1 and column 2. The elements that remain form our 2 by 2 determinant. They are 7, 2, 1, and 8. So, the minor of 3 is the value of this determinant. M sub 1, 2 equals this 2 by 2 matrix. Now, let's calculate its value. We multiply the main diagonal, 7 times 8, and subtract the product of the other diagonal, 1 times 2. This gives us 56 minus 2, which equals 54. So the minor of 3 is 54. Let's move on to the second element. We need to find the minor of 2. Locate 2 in our determinant. It's in the second row and the third column. This means we are finding m sub 2, 3. As always, we eliminate the row and column containing the element. So we delete row 2 and column 3. The 2 by 2 determinant that remains is formed by the elements 1, 3, 1, and 3. So the minor of 2 m sub 2, 3 is this determinant. Now let's calculate its value. Pay close attention to the negative signs here. We multiply the main diagonal. -1 times -3. From that, we subtract the product of the other diagonal, 1 times 3. -1 times -3 is positive 3. 1 times 3 is 3. So we have 3 minus 3, which equals 0. The minor of 2 is 0. Finally, let's find the minor of the third element, which is 1. The element 1 is in the third row and the first column. This means we are looking for m sub 3, 1. Following our procedure, we will delete row 3 and column 1. The elements that remain are 3, 4, 6, and 2. These form the 2 by 2 determinant for our minor. So the minor of 1 m sub 3, 1 is equal to this determinant. Let's calculate its value. We multiply the main diagonal, 3 times 2, and subtract the product of the other diagonal, 6 times 4. This gives us 6 minus 24. This equals -18, so the minor of 1 is 18. We have successfully calculated all 3 requested minors. All our answers match the provided memo. Let's quickly recap what we've learned. We learned that a third-order determinant is a 3 by 3 grid of 9 elements. We also discussed that the cofactor expansion method is one way to solve it, and it relies on understanding minors and cofactors. The most important skill we covered today is finding the minor of an element. The process is to first identify the element's position, then mentally delete its row and column to form a smaller 2 by 2 determinant. Finally, you calculate the value of that 2 by 2 determinant. This value is the minor. We've met our learning objectives for this tutorial. You should now be able to confidently find the minor of any element in a 3 by 3 determinant. In the next unit, we will use this knowledge of minors to determine the cofactor of an element. Thank you for watching this tutorial from Math Zone African Motives. Subscribe for more tutorials.